so this is your microphone, okay? Thank you.
So, okay, good morning, everybody. Can you hear me even at the end? Okay, I want to thank you, Professor Reis, and all the organization for this invitation. It's really a pleasure and an honor for me to be here. It's very nice to see you from here. I see it doesn't happen often to see so many people, good young, and with a good mix of gender too. So that's very surprising. So thank you very much. I will do my talk. We can be as interactive as we want, so do not hesitate me to stop me. And if you have any question or if you want to go deeper in what I'm going to propose. Okay, first of all, so as Professor Ray said, I work for ST Microelectronics in Catania. I've been working for that company for 28 years now, since 1997. And I am also recently a founder of a startup, which is in Italy. In this talk, this talk will not be very technical. It will be basically following the previous talk, but more in an entrepreneurial direction. Okay, so what we deal with, and I deal with now, is a complementary to what Professor Aiello just explained. So I'm trying to work on mass scale IoT. So what we try to do, both in ST as also as in Italy, to go in the mass scale IoT business. What is the difference, or what is the peculiarity of mass scale? In mass scale, we want to put really a large quantity of sensors. The idea is not to install 1 to 2 sensors, but is to install sensors in every room in this facility. And of course, you understand that we end up easily with thousands of sensors. And these thousands of sensors become a problem. I mean, even if the sensor itself is a simple thing, like I say, like cooking pasta for one person is something simple, but if you want to cook pasta for many people, it becomes progressively more and more complicated. So the maintenance of a few sensors is a relatively simple problem, but if we are going to have to go to millions of sensors, this is going to be a problem of maintenance, and also is going to trigger several problems: the maintenance of the problem, the cost of the sensors, and also the end of life of the sensor. So these are problems that are not trivial, that we are going to address with several different, in an holistic way, with several different technologies. So Italy is a startup that has recently been created, and the aim of this company is basically to deal with sustainable electronics. We believe that if we go to the mass scale IoT business with trillions of nodes to be installed by 2030, we need to be prepared to replace 270 millions of batteries every day in the world, even in the very optimistic way reality where the battery can last up to 10 years. I've never seen a battery lasting 10 years. But if you do the math, if you consider, let's say the battery can stay 10 years up running, if I install every trillion of node I install, I need to be prepared to replace 274 millions of batteries every day. And this is clearly unsustainable. Unsustainable from many point of view, which is not only ecological, because normally we basically think that sustainable means eco-friendly. It's not only that. Of course, replacing batteries or all these batteries pose an ecological problem, but also from the kind of materials that we need to drag, also from the cost of the maintenance, because if I go to the director here that is doing the maintenance, I say, you know what, you need to install sensors in every room because we increase the performance of the heater, the air conditioning, we get the better performance and so forth. I say, okay, good. But then I say, you know what, you need to put 10 sensors every room, and it does the math. It does the math and say, well, I need to replace 3,000 batteries in 3 years. I said, no way, I don't do it. So this is not sustainable. So our job is to make this possible. And we do it by using everything that, by using in directly into, so today, what already Professor Ayala has proposed before. So we are going to use, well, we're going to work in IoT, but must be ultra low power IoT, and we use sustainable sources. So we try to get the battery where possible. Of course, that's not always possible, but we have seen that in the majority of cases, going battery-free is possible. Most of the sensors might not need batteries, most. Not all of them, but most. So given 100 sensors, if I can make 70 sensors battery-free, or that means maintenance-free, or even if you want sustainable from ecological point of view, social point of view, and economical point of view. So these are the problems that we are going to do. So we need, in fact, to do sustainability in 3 different ways: social, ecological, and economic. Social, because striking materials is going to go to an end or to trigger wars, or social problems that we all know, but also, oops.
Just 1 second.
Okay.
Need to change it. Sorry.
It's okay.
There you go.
Okay. Of course, ecological problem. 274 millions of batteries to replace every day in the world is a big impact on the ecological and economic, because nobody will install thousands of sensors and spend thousands of dollars to replace these sensors. So we need to go and solve all these problems. And so the way we propose and what we want to do is to perform and design. So start from the design, from the thinking of it. Energy independent wireless sensor node. Sensors that are as small as this in some cases. So basically, I can show you what you can do. So this is a wireless node. This moment that is as long as it takes light, basically, and so they don't need batteries. They can work without using any battery. So, and we found out that this is possible. And as I said, we can cover 70% of the sensor. That sensor that is going through is a BLE sensor. This is instead using a sub-gigahertz telecommunication. So it's basically a LoRa or a Sigfox node. It's a prototype, so we are going to squeeze and make it small, a little bit bigger than that. And also this is possible with this to sense data. We have 4 sensors here. We have a solar cell, but it could be any kind of harvester. Not the solar cell is easy. I send here, I have a light, and they will start basically working. So that's the idea. So we go through that, not just replacing components, but all must be done through the design. So we need to think ahead. That's why we start from the silicon already. So we have a cooperation with ST Microelectronics, for which I work, where we're going to optimize our ICs in order to do that. What you see there is, or this product here, is based on a single microcontroller. It's the first prototype where a microcontroller is also doing energy management. Normally, if you want to do something like that, you need to put a power management, a DC-DC converter, a battery charger, microcontroller, sensors, radio, blah, blah, blah. This is instead a microcontroller that is embedding also a telecommunication unit, a radio unit, and is able to perform only by working on firmware, so not with analog. Still, the trend is going to do digital for many reasons, because digital is low cost, is flexible. So in this case, we are fully working on the digital domain to perform also power voltage detection. We are also performing energy management, everything by using a microcontroller without using external components. Why this? Because this goes in the direction making it sustainable in terms of the cost. The cost is important. Today, The cost of the wire sensor node is too high. Not many people can afford it, especially if you want to go to mass scale production to a very large volume. So the cost of the unit sensor must be low. So this is something that a designer must keep always in his mind when he's going to design a system like that. Let's make it low cost. And this is one of the problem to address. Having a low cost electronics is not that simple. And you need to start with that by design, not just trying to negotiate in prices afterwards. But you need to think what is the best strategy to go to the design. And we got that through the digital. And also, by pursuing this way of thinking, this philosophy, we also can make the size smaller because we have to embed less products. We can put everything in one single integrated circuits, and this makes everything also smaller and low volume. Low volume is important. So a sensor normally also is required to be small. What you are seeing here is a wearable sensor. It's a 2 by 2 centimeter sensor with a very small solar cell. So how to make it small? Well, first of all, if I want to make this photovoltaic cell smaller and smaller and smaller, first of all, I need to go to low power, low power, low power. Because if my integrated circuit is really low power to go to the nano power, I need the less surface to catch the same light and the same energy. So everything starts from the silicon design, not afterwards. So you need to solve all the problems before. So knowing what to put into silicon, that when you do choose the right test chip. As of today, we were thinking that this kind of work was something like research, pure research. Well, there's still a lot to do, but what we demonstrate with this kind of prototype, that off-the-shelf devices are not ideal, but are good enough. They can be better. Of course, as I said, let's make it, let's reduce the power consumption by using all the beautiful techniques that the Professor Oriazzo already just explained, and we can reduce the size of this solar cell more and more. Or maybe we just can take the different temperature that we have in a shirt like this from the body to the air. And that with a very small difference in temperature, we can make, for instance, enough heat that we can translate in energy. And if the power is so low power, we can go through that. So all this is triggering business opportunity that we are catching. That's why in Italy, that's why also ST is investing on this kind of technology. So Italy came for this idea to spread out all these ideas. And this is a business that I think you young guys can pursue as well, because there is a lot of volume here. There's a big demand there. And once it is going to roll over, is something that it could be interesting. We found it very interesting because the idea is to have an holistic way to solve all the problems, not only the electronics problems, but also the end of life. As you can see, one of the parts that I showed you is packaged with cork, and this is not just something that comes out by chance. Why cork? Well, cork is a material that is sustainable, is relatively inexpensive, and also has got a lot of electrical good properties. Cork could be the substrate for where to print the photovoltaic cell. It could be the dielectric of a capacitor. It could be the substrate for the antenna. In other words, the idea is not to use the cork only as a package, but as a material for building on it components. And somebody in Cork, Ireland, is studying this kind of capacitor successfully. So this is very important. So how we want to achieve sustainable electronic in mass scale IoT? Well, the problem is that one of the problems that we highlight is the wire sensor node maintenance, as I said before. I need to be prepared to do the maintenance of trillions of nodes. It's not that simple. And the second is ecological sustainability. Well, the solution we see is ultra low power electronic devices. And this is starting from the IC maker. It's not starting from from a startup. The startup can trigger the demand. The startup can pose the problem. The startup can provide guidelines and specification. But the IC maker need to go ultra low power, possibly nano power, which is going to be increasingly difficult because nano power is basically already the self power of any CMOS IC at the moment. Leakage is creating nano power. So we are going to hit to the bottom, which is the leakage. So we need to go and solve this problem. And this is going to be worse and worse because we are going, if we go to advanced the digital processes where we want to fit more and more stuff into the digital, the leakage is going to increase more and more because the more we go to faster design, the more we decrease the length of the channel, the higher will be the leakage. So this is something that technologically we need to address. Okay, so how as to which are the requirements of a nodes like this or the one that you have in your hands at the moment? Well, it doesn't have to have wired connections, maintenance free, low cost. Low cost is important. It's not a trivial problem from engineering point of view. And so this technology has to be performant, but at the same time low cost. The two things normally don't go together. Okay, the more I increase the performance, the higher is the cost of the technology. So as engineers, we need to find the right trade-off. And also compact form factor, as I said before, and environmental friendly. So the key feature of this kind of nodes, we want to get rid of batteries, not because we have something wrong with the batteries. You see, this stuff here is a very advanced battery. So this is a new battery. So I don't like to say battery-free, because the problem is not against the batteries. The problem is against the batteries that don't last long enough. This is a solid-state battery. So it is produced by Iton, and this is a very advanced technological product. It's a battery that is solid-state, so the anode and cathode are solid, and they can last longer. So they can last 20 times longer than a normal lithium battery. And this is the power density, the energy density of this device is comparable to this bulky device that you see here. So there are progresses that are coming from several sources. And this is important because we are trying to collect all of them in order to create products that are more and more competitive and more solve all the problems that I told you. So the one you see here is the one that is going around. This was our first product. It's a 2 by 2 centimeter. So at the beginning for us, it was almost unthinkable to create a product, battery-free, which is so small, with a tiny photovoltaic cell of 15 by 15 millimeters that can work in an environment like that, where we have about 400 lux. So this is possible by using a BLE connectivity, and this is also possible by using off-the-shelf devices, which was unthinkable 5 years ago. Okay, so today we have devices that allow progressively to us to do this kind of products, and this is the good news because, as I told you, from the entrepreneurial point of view, you can now move from the mindset that what is research can become a work. So this is what is nice in the industry. So we think that energy harvesting or sustainable devices are something like that have to stay in the university. It's not, because now we have products in the market that you can buy, and there are begin this kind of activity. So in Italy, it's just a starter, but I hope to see in the market many more. So the system has got just a BLE connectivity, which makes it very easy, the readout, because it's simple. I mean, you just have to write a few lines of codes to create an app, and just can have the data from the sensors in any portable device that we all have in our pockets, like iPad or smartphones, etc. So This is a very economical situation because we can just have to do not a big infrastructure, but just a simple app that it's easy and cheap to do. Now, of course, what we can do with that? Well, the BLE communication have a range, has a range about 20 meters. So it's good for a limited environment, like an house. So for home and office automation is the ideal situation where I can just have this small sensor just stick in any wall, in any corner, and I can understand what's going on there in terms of temperature, relative humidity, presence of people. I can, for instance, we started with this product just triggering the lights externally, because this system is basically posed in an external world. So every day is taking the light and is communicating to an internal relay, and the relay is not turning off the lights. When the system goes out of energy because outside is dark, so it's not communicating any longer with the relay, and the relay understands that it's time to turn on the lights off. So in other words, I've done a twilight switch that compared to the state of the art, does not need any cable, does not need a complex installation. I don't have to call the electrician to post the wire, to drill the wall. I just can buy on the market, stick in the wall, and just install the communication with an internal relay, and that's all. And more than that, I don't have to take care of the battery replacement for forever. And the reliability of this object is about 20, 25 years. So for 20, 25 years, it's gone. And 20, 25 years is basically the obsolescence of any technology. Yeah. So I solved a problem in a very, very easy and elegant way. But not only this, I can modulate the lights. I can modulate the window shield, etc., etc. Just with the most simple system that we have, because I can control the lights. Well, this is very well required in Italy. We have a museum with a lot of pieces of art. And any piece of art, they're now triggering the idea of doing the restoration, predictive restoration. So normally now we wait that something is broken and then we fix it. The idea is that if I can put a sensor, I never go to the point where it is so broken that I need to stop. So maybe I can understand that the picture is not well in the right place. It doesn't have the right temperature. It doesn't have the right light. It's exposed to too much light. So we are putting in a piece of art sensors like presence, so that, for instance, a director can understand how many people is looking at that piece of art. Maybe it's not in the wrong place. Maybe they need to do, or the temperature is not right. The relative humidity is not right. And in this really moment, while I'm talking to you, we have a Caravaggio that is moving from Rome to London, and the sensor like this is basically tracking the temperature and the humidity along the way while it is inside the aircraft and so forth. So, of course, this wasn't possible before. I mean, nobody wants to wire into a museum with thousands of these. So nobody wants to wire all these sensors, and nobody wants to put the batteries that they have to replace. So this is, in other words, what I'm trying to say to you, that this kind of different technology is triggering new idea and new business that are endless. So from the point of view of being an entrepreneur, it's a mine gold. It's going to be a mine gold. Another thing we are doing now is agriculture. So we are very active on this field. Because why agriculture? Well, agriculture is the very next business, is the very next industry. So if you see all the agriculture is an industry, and if you see all the industry, agriculture is really behind in terms of technology. So the idea is to go there and provide a new technology, but the numbers in agriculture are huge, are very big. So there is a very before going to there, we need to solve the problem of the end of life, because people in agriculture, then we cannot afford of trashing electronics that is polluting so easily. we need to solve the problem of materials, and we need to solve the problem of communication. Now, this is a solution very interesting because what we do is here is not only using a photovoltaic cell, but we also use a microbial fuel cell. Now, in other words, it's well understood that into any soil, in basically every soil in the world, there are bacteria that they produce electrons. So they're called electrogenic bacteria. So what we try to do is with a couple of electrodes, we basically collect these bacteria and we get the energy to power the sensor night and day. So it's a very cheap solution. It's a very cheap solution. That is what is required in agriculture, and we can monitor the plant. Moreover, it is understood that bacteria produce electrons more or less in function of their health. So if the plant is going to die, that means the bacteria are going to die. So the power that we can extract from the soil is lower and lower. And from this, we can understand how the plant is behaving. So in other words, I not only have a sensor, but also or extract the energy. I can reuse the harvesting to monitor the health of the plant. So this is very powerful, and we are investing and working a lot on that. And this is very, very promising. Just a can of can like this, full of soil, can provide energy to power this sensor. Okay, so I don't need you, and the technology is scalable. If I put 1 cubic meter, I can power an LED lamp. Okay, that's very interesting. And as I said, we are investing a lot in agriculture because all the economical indicators have a good trend, very steep trend, and is where basically there's business. I mean, companies like ST, they look for business. Of course, they need to have rewards, but also startup needs to go where is no research. So it's a matter of business and getting money. So this is another idea where you see where we basically posed with the sensor that you are having in your hands in the moment, we have done the monitoring of a knife. This knife is a Mexican knife, where in this case, the monitor and the energy is taken from the plant. You see the plant on the left, they are producing the energy. So we don't have any solar cell. The harvesting is coming from the bacteria that are into the soil. And the plants are important because in the soil, the bacteria can survive as long and produce electrons as long as they have something to eat, so something to metabolize. But if we don't put anything into the soil, little by little they eat everything and nothing is left to them. So at the end, the bacteria will begin to die. Putting the plants instead means that what we do in the laboratory is just take a glass of sugar, we put it into the soil, and they survive. But of course, this is a maintenance operation that we do want to do. So putting the plant instead is producing glucose as effect of the photosynthesis. So still is a solar system. So everything starts from the solar. So the solar is producing the photosynthesis, they get the glucose, the bacteria get the glucose, and once they have the glucose, they produce the energy. This is true as long as the plant is in a good health. But if something happens, I can understand because I have less and less energy. I get less and less energy from the plant. I can monitor the energy, and I can understand that something is going wrong to the plant. Now, a really ambitious but feasible project that we are pursuing is to change completely, to do a revolution into the irrigation. And so today, irrigation is based on an empirical way. I have a grass like that, and normally I tell you I give 20 minutes of water every day. I don't know if it's the right thing or not. I never understood. I decided once, empirically, that 20 minutes was good enough. And as long as I don't see the grass dying, I don't care. Maybe I providing a lot of water. I don't know. So what we want to change is completely the paradigm. So what if the plant can call me and say, hey, you know what? I'm thirsty. Give me some water now. And so an electro valve can give the water. And then you can say, I have enough water and I don't want the water any longer. So in other words, it's not empirical, it's scientific. I'm dosing the water in the right way. And this system studies demonstrates that they save 40% of the water. 40% of the water in a field like agriculture, where the water consumption in the world is 85% of the water is going in agriculture. So we save 40% in where really there's a high consumption of water. And this is possible. So because now with this technology, I can disseminate sensors. I can put the sensors everywhere because I don't have to care how many batteries I need to replace in 3 years. So I can monitor the grass, and the grass can talk to the water control system. And you know what? What we did is that also the water control system is without batteries. So today, if you take any water control system, they have a battery. We did it battery free. And actually, we did it with a Clubber that is one of the most known brand in Italy for, it's also known worldwide for a water control system and gardening tools. So what you see there is Aqua Solar. The system Aqua Solar is the very first water control system that is battery free. At the moment, it's based on a photovoltaic cell, but we also have tested one with a turbine. So we have everything. So we have all the systems, sensors, energy harvesting, ideas, to go from an irrigation system that is empirical to be scientific and go and save up to 40%, if not more, than of water. So this is what we have, and now so the water control system is already out on the market. You can buy on the internet. And what you see, the sensors are in progress. We are making all the sensors that can communicate to the plant in order to say, hey, you know what, I'm sick today, I need water, I don't feel good, call a doctor, whatever. So that's the idea. So if you have a problem with your plants, think about this. So these are commercial solutions. In order to do that, we use, as I told you before, exclusively microcontrollers from ST Microelectronics. What you see here, this is for BLE. We use the STM32WB from microcontroller. WB is integrating, is embedding a Bluetooth Low Energy radio. So you have everything in one chip. You have the microcontrol system to communicate with the sensors. We have inside the energy management for energy transducers. We have the radio. All this is not there by chance. It's coming from understanding the customer needs, understanding the technology, which are the problem to solve, and then you go and define an IC, an integrated circuits. And if the integrated circuits is good enough, then you can go and solve all the problems that I showed you before with creativity. Okay. So another thing we are doing in this, and this is with a cooperation also with Professor De Marchi of Politecnico of Torino, we are doing the in vivo monitoring of the plants. So what you see here, unfortunately I don't have, I don't know, oops, okay. You see in the stem, you see there are two wires that are into the stem of the plant, and the stem of the plant has a variable impedance. This variable impedance, it depends on the health of the plants. Of course, if the plant is that stem is a piece of wood, and the impedance is infinite. If instead the plant is alive and there is a good, is in good health, there's a big flow of ions through the stem, and of course the impedance goes low. By monitoring the impedance, agronomist people can understand several different things about plants. And this can be done by disseminating sensor. I can put one of these in a plant, and basically I can understand if the plant needs an help, I need to call a doctor or whatever. So solving problems in advance. Again, Professor De Marchi, with this technology, he took in a scientific way two different, two apple cultivars, the same size and the same place, but they divided it in half, Half was irrigated with this kind of technology, and the other half was irrigated the way normally farmers do. Well, the result is that at the end of the year, they got the same the same the same harvesting, same quality, same size of both cultivar, but the one that was driven with this technology saved 40% of water. Actually, 44. Okay, so and they also understood that the water was needing the water when the farmer was not even thinking of providing water to the plant. So there's a lot of understanding, but there's a lot of improving on this. So, but we understood that to go, as long as we stay in a small area, Bluetooth Low Energy communication that has a radio of 20 meters is okay. But in farming, the highest that we could get is 160 meters, which is not enough for very large cultivars. Therefore, we are going to work also with LoRa, that is a long-range communication. Or in other words, we're going to work with sub-gigahertz, because sub-gigahertz means that you are working at 1 gigahertz instead of 2.4 as the BLE, so the range of communication increases. And now we have standards like LoRa or Sigfox that have really low power. So everything starts from having a good communication. So we can communicate up to 15 kilometers, not 20 meters, with a reason by using a simple system like this. Okay, so this system can go up to 15 kilometers. So, and this is important. This is the node with a compact view of the node. You see here, there's a microcontroller. Oops. The two yellow box are basically low voltage capacitors. So for immediate, to provide immediate energy. And here, what you see here is basically the antenna, the photovoltaic cell, the node itself, and something which is peculiar. This is another good news that is coming from Sweden. In Sweden, you see that the gray, the gray square is basically this one. Which is a supercapacitor. Look how thin is this. This is a supercapacitor of 1 farad. And you know what inside of this is wood. So that's the good news. Sustainable materials can make sustainable electronics. So this is a really good example of having a very good 1 farad is this one. So low volume, good energy, and sustainable, because end of life, I have wood here. Okay, so that's all we are searching for. So integrating technologies that are sustainable to provide sustainable concepts. So sustainable irrigation, sustainable agriculture with sustainable electronics. What you see here is a device that basically is with sub-gigahertz connectivity, and there is a sensor. The sensor you see in the bottom is a chemical sensor. In this case, is an ammonia sensor that is used inside the farming for chicken, because they understood that by controlling the level of ammonia, the chicken can grow up better weight. Okay. So you see here, the applications are endless. So I'm writing here what we are dealing with, but every day I have one extra application. So it could be farming, it could be controlling of people, controlling of cows, or even a piece of art. So I don't go. What we are trying to do, in any words, is to address all the problems. And problems are coming from sustainability. That's why we use packages that are in cork, as I said before, because cork is not only material for packaging, but it's also good material for creating components, okay, as well as wood, okay, as well as wood. So again, in sub-gigahertz, it's not that difficult to get the data. Just having applications like LoRaWAN or Sigfox, they basically enable to have any kind of dashboard where you can see all the data and can get any kind of actions. This is something we are starting to invest. It is again a very good news. Now, we not only sub-gigahertz communication of BLE, but even satellite. So I can, with this board, by using the antenna that you see in the picture, I can basically communicate and send my data to a satellite, so to a low orbit satellite. So that's very good news because that means I can disseminate even more. So now with this, I can really put sensors in to monitor phenomenon in mountains, hills, and wherever. I don't want to go. I want to go once in my life. I leave the sensor, and they will communicate with the ops with the satellite. I get the data wherever I want. Okay, so with this, I thank you for the attention, and there are several takeaways. The message I wanted to show to you today, especially you that are students, the energy harvesting or IoT, the mass scale IoT. So today we are used to IoT, but really we are not going to high volume. It's a very good entrepreneurial opportunity because the technology is ready already. It's accessible. We have off-the-shelf devices that allow us to do that. So I thank you for your attention, and that's all from my side for today.
Question? Yes. Professor, is the growing conversation of AI and also the definition of AI and I saw in the slides to apply this concept and I feel positive more about
Yes, I thank you for this question because it's actually something I forgot to. It was there. I forgot to go deeper. Thank you very much. Yes, AI it's very challenging as of today, but we are working on that. We are working also with Professor Aiello. It's the research. Okay, so it's not. What I said before. It's done. So you find it on the market. I can show you today. Okay, AI it's to be trickier. We know how to do it, but we need to prove it. But we know how to do it, but we have to do it. So we are working on that. So we have a couple of researchers that are working actively on that. It's quite tricky because the idea is that I take a picture on the field of the plant. Of course, I don't want to send all this data. I cannot do it. So I need to elaborate on the age, and the processing that we do is the same as transmitting. So the idea is that we can't, we don't want to transmit any minute. In some cases, you can't, okay? Because you have a limited kind of number of messages. In Sigfox are 144, and LoRa you have basically a limit for the safe use operation of the LoRa communication. I'm talking about LoRa because I believe this AI is interesting when you deal with, I don't know, agriculture or stuff like that. So, but if there is energy, I still getting energy. So I have energy that I can store. So then when I have this energy, I can use it either to send the data or to process the data. So the concept is the same. Now, the thing is that processing the data requires energy. So I need what we are going to do is a trade-off of sizing the capacitor to do everything in one shot, or maybe we can stop it at a certain point, and basically the processing of the data, we harvest the energy, we reprocess, and up to the point that we finish, and we are able to send it. So poses some challenges, but we are going to manage it. And I hope the next time we meet, I say to you, I have the solution, but we're working hard on that. So thank you for this point. Very good question.
other question? Yes.
Well, thanks again for the talk. You stressed highly on the point that we can use this, we can use harvesting right now in IoT because we have off-the-shelf components. That's great, right? But at the same time, do you see a good link, a good partnership with ASIC developers to actually, something more advanced that you still, you know, you can still see some holes in the project.
Yeah. Yeah, not only I see it, but I live it because I work. I go from to the applications and see the needs, but I also drive specifications for the chips, at least in ST. But I know that also Synopsys, other major companies are working on that, of course, and that's the future. I mean, today, addressing AI without thinking about the power consumption. Okay, yes, you do a very nice, neat, and powerful node, then it's consuming too much. So you can use in a limited situation. What we want to do is to go to mass scale. So today, if you see the sensors, the marketing is stuck. It's basically saturated because I cannot put today more than 4 sensors in this room and the next room. What I want to do instead is I want to put sensors everywhere. That is will make the sensors fly. But AI is related to sensors. So if you don't have an AI that is portable or you can disseminate it, yeah, it's a good idea, but then I don't use it because then I have the problem that is consuming on age. I have to transmit, and the battery I need to change not in 3 years, but in 1 year. When it's like our mobile phone, we went to put more and more stuff, then we need to charge to charge the battery twice a day. That we can do that because it's a mobile phone, it's a portable device, but you can do it if you want to do sensors. No, it's not possible to do that.
Okay, thank you very much.
Thank you very much. Thank you very much.
We are late in our schedule, so now it's time for Mr. Greenblatt to do his presentation. So Peter Greenblatt is the head of CMOS Chile. So some of you want to work in Chile, you write presentations and go to the and Victor is also a member of CASS board of government, and also the head of the chair.
There you go. And the cable is here, actually.
So Victor, the floor is with you.
We're
Tu viste onde é que foi parar o cabo? Cadê mim? O cabo da TV.
cabo da TV, right?
So I will show.
Ah.
Okay. Try this one.
Okay, so
Yeah, it's not very long. It's very... But don't worry, you could just like put it in the stream here, and then I can like I'll manage it with closer like this.
So waiting for the setup.
No, because you connect it.
So as you know,
You have to open it again. It's,
end of August, we
No,
have
but
the
don't worry about that, that
issue
doesn't
of
make-
the GP. So SPCCI, Instituto, Auditorium, CASS workshop and so on. That this year will be again in Manaus. And then
Oh,
we
okay.
have, in the German edition. So you have to end of March, beginning of April, to submit your papers. And as you go also, you have a paper in SPCCI. You can, the students are able to request for the site for that. The only thing that you need to be a member of CASS. If you are not yet a member of CASS, it's time to join CASS. So as you know, the membership is valid to the end of the year. And this year we have several events sponsored by CASS also here. So we have also in the end of April in Fortaleza, the first edition of the Latin Conference on IoT. It is sponsored by IEEE IoT Technical Community, where CASS is one of the sponsors of the IoT Technical Community. Like, tomorrow to describe already
you have
we
to
have
choose
last
J as well?
year, you can already prepare also your agenda to submit
So J for an HDMI and then for USB.
Arequipa, Peru, very nice location, so the general chair will be here this afternoon. Dr. Carlos Silva, that will be talking about the CASS opportunities. And then this last talk of today will help us if you are not yet convinced in the name of CASS.
Não tá precisando de novo o HDMI. Não sei por quê. Não tá precisando de novo o HDMI. So how did you guys fix the HDMI before? Did you use the VGA cable with the adapter?
I use both. I don't know which one. I use both.
None of them is working again.
I use both VGA and HDMI.
Let's try it out with
You need a station?
Actually, I'm not sure if it's an adapter. Maybe it's just like we don't know which cable is actually working.
And that's why I plug both.
You tried both?
And one with VGA and another one with HDMI.
Okay, can you borrow it, please? It is.
I plug both.
Oh my god, this is like all types of things. There you go. Let's go to
And also the other two.
worst comes to worst.
Also the other one. There were two, right?
Yes, there was the VGA.
And VGA also, plug VGA. Also use that one. Plug also VGA.
Just to make sure. And without the adapter.
I don't know which one. It was this way, okay?
Boom. Still not. So we'll not be able to transmit it as well. It's just like the first one.
Okay, so we will start now after the small problems, the technical problems. So
Let's go.
I'm going to talk about low power digital IC design. I know that my colleagues were talking most about analog. We're talking about digital now, which is not just press button and get the result. It's a little more complicated. We can discuss that during lunch, okay? So, first of all, let me present in 2 minutes the company I'm representing. So, Synopsys, and we see that today there is a lot of changes across many industry, and we are trying to provide the technology to empower all of those innovators, all of those people that will have this access to many industry. And of course, IoT is one of the important part of this change in the world. So Synopsys, what we are looking, how we got there is by, this is the change we have done over the years since 1986 when Synopsys started. And we see that we have been able to increase the productivity by 1 million during this 30 something years. And just to go straight on that, so we are leader in software automation for design. We are present in several countries in the world, and okay, we are more than 20,000 employees. More than 27% of the income is reinvested in R&D. And another important thing is our university program that we call SARA, which is Synopsys Academic and Research Alliance, where we try to collaborate with several universities. There are several here in Brazil that we are collaborating with different things. We provide the tools. We also have some partnership on education. We also have some academic ambassador program and so on. So let's move on because we're a little late on that. So what I want to discuss today is some background, and after talk about the digital IC design flow, power, the problem of power, and how we can, what are the techniques that will help to reduce the power on digital design. Even that some techniques can also be applied for analog design, but mostly there. So the first thing, okay, is when I skip. The first thing is that today we're using chips everywhere. Everywhere. We are having chips on a daily basis. We are interacting with chips daily, and we can think in a lot of application. Now we don't talk anymore about a car, but we talk about a computer on wheels, medical devices, and so on, so on. IoT, agriculture. I have been working also with Professor De Marchi, that Roberto was mentioning, on IoT for agriculture, and so on, and so on, so on. And the macro trends that we are seeing today in the market is that the software is driving differentiation. So companies are doing software to differentiate from others, but chips make that possible. Without the chips today, there is no. So, and today we need more and more specialized chips. We need more and more our own chips. And we see that companies that in the past were not producing chips, today they are doing. We see that Microsoft is doing their own chips, Google, Facebook, and all those guys working on IoT, they are doing their own chips to be able to produce that. So optimized software and chips are key to system success. And this is the beginning. The first transistor that was created in 1948. We know that. And after we go to the first integrated circuit and the MOSFET that was created in the 70s. And we have a lot of invention that produced this electronic revolution. And this is the two picture of the two first integrated circuit. The one on the left is the Robert Noyce that is still used as technology, it's a planar technology. The other one is the Kilby's one that is no longer used as technology, the Kilby's way to do as an integrated circuit. And advancing IC technologies, we move from a few thousand transistor to what we have today, which is the Cerebras, which is trillion of transistor into a wafer. This is one chip in one wafer. It's the complete wafer is for only one functionality. And we see that the technology today is a CMOS converter. So we are still using CMOS, even that some people are saying, yeah, CMOS, we have to change. We are talking about silicon carbide and other kind of technology.
Sorry, I just had to change profile.
Okay. So I can think now. No, I'm saying that CMOS is still being used, and we have been changing transistor, the technology, to adapt to the new technology. So we move from the normal, the transistor to the FinFET and all gate around and all that, but we are still working on CMOS technology. Okay? Okay. And the Moore's law, we all know that is, I have been listening for years that the Moore's law is over, but we are still doing the Moore's law. And Moore, first of all, was an economic law, was not a technical ni a scientific law. He said the number of transistors in IC will double every 18 months at the same price. And that was the important part of this law. And we have been, and he never said it has to be on one surface. So 3D is another way to continue with the Moore's law, 3D and so on, and even chiplet. So it's a way to continue doing that. Die size has been growing through the last few years, as you can see in this picture, how we have been growing the die size, grows by 14% every year. The frequency has also been increased every 2 years. That was creating some issues on power, because power is related to frequency. There is a direct proportional. So this is the reason that at the moment we start talking about the dual core, quad core, because the frequency, we were not able to continue increasing this frequency. Okay? And the power dissipation, we can see that how it has been evolving over the years, the power dissipation, and this is why, and we say the power increase about 10 times every 3 years. Okay, 10 times every 3 years. And we see, for example, we look these kind of devices, and we are desperate that because we have to plug the device to get some battery to continue using it. So yesterday night it was very fun, because in the hotel I don't know who did that in the hotel, but the only plug that was available in the room was connected to the light. So to have power on the plug, I had to switch on the light, but I wanted to sleep. But at the same time, I wanted to charge my cell phone, my watch, and all that. So it was really crazy. So we are desperate for power. Okay, and what are the design challenges today? So we have some microscopic problem and macroscopic issues. The microscopic is related to the market, or time to market. We need to design very fast. Our competition is changing. I look at the cell phone, or even the application on artificial intelligence. Millions of gates, high-level abstraction, reuse and IP, predictability, and talent availability. According to McKinsey, by 2030, the lack of talent will be 1 million professionals in 5 years from now. 1 million persons we will be lacking 1 million persons. But on the microscopic problem, when we go into the design itself, we have ultra high speed design, interconnection, noise, crosstalk, and the more we reduce the technology, more we are having this kind of noise and crosstalk and reliability and power dissipation and all that. So we need to increase the battery life, because the problem we have as designers, so I'm taking that from the designer point of view, we don't know how to do harvesting. Someone will give us the power, but we need to increase the battery life. We need to increase or to reduce the consumption of power to be able to use what we have. As I say, as designers, we don't know how to increase the battery, or how to. So one thing is to increase the battery life through the use. How I can reduce the consumption of the battery so I can do more. And low power, circuit design importance. We know that there is the evolution of batteries. We can go to solar panel and so on and so on. But again, the designer will concentrate on how much power we dissipate, will not concentrate on how much power we are going to get from the battery. This is a different problem. What we do is, based on a battery, we do a computation, how long I can use that battery with my design. So application area for low power electronics, so you can add whatever you want here, because it's everything today. It's everything. Even computers, we are talking about low power, because we don't plug the computer really very often. So the power source, as I said, batteries, that we use the batteries. that convert the chemical energy into electrical energy. We also have, so we have two kind of batteries, the non-rechargeable and rechargeable, okay? But on the other hand, when we talk about, for example, agricultural application, we cannot go and change the battery very often because sometimes it's very far, or sometimes it is on the collar of an animal. So it's not easy to change the battery, or even a pacemaker. It's not easy to change the battery on a medical device. So we have to consider that batteries are good, but however, we have to take care of how long we can use them. Other kind of sources are, okay, solar panels, and so on, so on. There is even some application, they are generating energy for electrical cars when they go through at the traffic lights. When the car is there, they are generating also energy that is transferred to the battery of the car. So vibration-based power generation and other possible power source, thermal and so on. Okay, so what time I have to finish, Ricardo? 12, 12:30? Okay, so let's go now to the design flow, the digital IC design flow. So first, let's start defining what is a digital integrated circuit that encompasses both combination and sequential logic. So a digital circuit is a combination of digital and sequential logic. A combinational circuit is defined as an electronic circuit where the output is solely determined by the current inputs. So this is a combinational logic. Combinational circuit, the output of the circuit is depend only on the inputs of the circuit. By difference, a sequential system, the output will depend on the inputs and the state of the circuit. So it keeps the history of the circuit, and this is the reason we have what we call the final state machine and so on. So the output of a combinational circuit just depends on the input. The output of a sequential circuit is a combination of the current state of the inputs and the previous state of the inputs. There is another definition, the register transfer level, that is important to know because we always say that a digital circuit starts from a register, an RTL file. So it is an abstraction for design where the designer will describe the circuit or will describe the functionality the designer is trying to implement. It's normally designed captured using a hardware description language, could be Verilog, System Verilog, VHDL, now even System C and some other languages that are used. It is based on synchronous logic and contains three primary pieces. The register, the combinational logic between register, and the clock that will control the state changes. And it is important to understand that when we talk about synthesis, not high-level synthesis, when we talk about synthesis, on an RTL, the RTL will not, and the synthesis will not generate the sequential part. It is generated by the designer. The designer will define the sequential part. So in an RTL design, a circuit is described as a set of registers and the combination and the transfer between those registers. This is the reason we call that register transfer. In general, what we do is we have a cell-based automated design. So we have a library. We have the library depends on the process, depends on the fabrication, depends on the manufacturer. The manufacturer give us the design rule, the PDKs, and so on. We write our RTL. We go through EDA tools, okay, and we get the design. This is the press button, but it is not so easy. There are a lot of things to do in the middle. So we have an idea. We have an idea. We specify the idea. We put the goals and constraints of the design, the functionality we are looking for, what the chip will do, the performance figure, like for example the speed and power. We say I don't want to dissipate more than, I don't know, 20 milliwatt, 20 watt, or whatever. The technology constraint, like the size and space. I need to define how big would be my circuit, and the fabrication technology. And this is very interesting when we design the fabrication technology, because at the moment that synthesis was created almost 40 years ago, one of the main ideas was to be independent from the fab, meaning that I want to write an RTL and I want to try different fabs. And people were doing that in the 90s. So fabs were not happy because through the synthesis, there were a comparison between, for example, Global Foundries, TSMC, technology, etc., etc. So this is the reason now you have to define from the beginning which technology you are going to use, because if not, you don't have the PDKs. Because the PDKs belong to the fab, so you get an NDA and you get the PDKs because the fab is giving that to you. So the RTL, we already defined that. It includes logic representation, final state machine, combinational logic, sequential logic, and of course we have to verify that this is doing exactly what I'm planning to do. Let's say that I'm generating a processor. I want to verify that an addition 2 plus 3 will give 5. Because if I don't verify up front, I will have problem with my circuit. Then after I build a gate level netlist through synthesis, consider specified constraint and the library that I'm using, consider constraint for optimization. So we optimize synthesis, we optimize the netlist for speed, for size, and for power, but will not optimize the functionality. The functionality is done by the designer. And it's completely structured and will convert this behavioral description that is the RTL to a structural description, which is a combination, it's a net, is a combination of gates and their connection. And then we go to the physical implementation that we want to convert a netlist into a layout, a geometric representation, and it's called also the layout of the circuit, as I say, and it's modeled. There is 3 sub-steps of that floor planning where we define where the big blocks will be placed, and after we place all the cells, and then we route. And it produces a GDS2 file or any other format to send to the fab, and a physical verification has to be performed. Because sometimes, even if the tool is producing what you expect to produce, you can have some design rule problem, you can have some speed problem, you can have even electrical problems. So you have to verify your design before sending to the fab. And this is the file used to fabricate. So the basic step on a digital design, so you have the specification with the example there, X equal blah, blah, blah. You get the gate level netlist, and then you get the layout. And the complete flow for a digital design is all that. So you do verification, you do synthesis. Into synthesis, you can put design for testability, which is adding some special cells to be able to verify your design when it is fabricated. Because you can imagine that when you have millions and millions of transistors, you cannot put an oscilloscope or a voltmeter there. So you have to have ways to verify that your circuit is working correctly. You can also have formal verification to verify that the synthesis is not creating any issue. You can also do some power consideration we are going to talk later. At that level, we start improving the power. When everything is okay, and you do some static timing analysis to verify that the time you are asking it's met, meaning that let's say that we have a clock of 1 gigahertz, we have to verify that all combinational paths can be met, can be fit in this 1 gigahertz. And then you go to the physical part, the floor plan, the placement, the routing. You do a lot of verification as well. You do again the static timing analysis with the real parasitics of the circuit, and then you can breathe and send it to the fab. Normally, for a design, it will take 6 months to do all that, or maybe sometimes even more, with a team of, I don't know, in big companies, 50 to 100 engineers working on that. There are engineers only for verification. There are engineers only for synthesis. There are engineers only for place and route. So they specialize themselves in this kind of domains. Okay, let's go to power now, which is what is important. So this has been the power consumption trends. We have been increasing the power consumption, and if we continue in the same way, we will, and we already can do some X into my computer. I can do some X in my computer, and we have been putting fans on computer, on data center. Today, the bill of electricity in a data center for cooling the data center is much higher than the bill for the computers. So we are spending a lot of money on that. And what are the problems on power? We have the low power first. This is the first problem. We talk about low power. And why low power? Because we want devices to be able to work alone and to do not, we don't want to plug those devices. But not only the devices that are on batteries, but also the devices that are plugged. Energy production is the most important producer of CO2, greenhouse gases. So, and it's around 40%. The second one is agriculture, by the way. So if we don't reduce the CO2 emission on the energy generation, we're not getting any result to be sustainable. Okay, so even when we plug a device, we are spending. So this is the reason also we need low power everywhere. There is the power efficiency. Okay, I don't want to waste too much power because, as I said, it's expensive, or it's also producing pollution and all that. And reliability, I need this mostly for design under 90 nanometers. Okay, there is a funny story because when I was a student a long time ago, my professor told me CMOS is wonderful. There is no power consumption on CMOS. Nice. So what was the problem? At that time, we were working, wow, one micrometer. Okay, now we're at 2 nanometer. And the problem is the following, and we will see that, okay, let's go to the next slide and see. Okay, this is the problem. Where is the power dissipation in CMOS? You have two parts, the dynamic and the static part. Dynamic is mostly, and the most important part of dynamic, and when you have a transition from 0 to 1 or 1 to 0. Okay, and there is also the short circuit. There is a moment, very small moment, very short moment, where both transistors are conducting when they are changing, so there is power there. And the second part is what is called the static power, which is leakage current and fabrication issues and all that. So until 90 nanometers, some 180 to 150, the static power was almost zero. So we were taking care of the dynamic power. But then we got under 90 nanometers and the static power become very, very important, even more important sometimes than the dynamic power. So we start to take care of that. But it's very complicated for a designer to take care of that because it depends on the manufacturer. And this is the reason, so we change and we create the FinFET. Because FinFET, one of the reasons of FinFET is to reduce this leakage current. And then when FinFET was created, we went back to the dynamic power. And then we went back to the static power. And then we created other kind of transistors. So this has been for the last 30, 40 years. But CMOS, for me, was perfect. No more. Okay, so this is the four components of the power dissipation. And you can see that two components are dynamic and two components are static. And a designer, I come back, can only take care, really, a designer can only take care of the dynamic part. The static part, a designer cannot change because it's based on technology. So this is the reason that when you talk about designers or when you talk digital design, not that, and when you talk about the EDA companies, they do a lot of things for dynamic power, not static, because we cannot think. There are a few things we are doing on static, but very small. So the switching power, this is the first one, which is when there is a transition from 0 to 1, 1 to 0. This is the most typical, and this is the reason that we are saying there is no power dissipation because transitions are very fast. The short circuit power, I was saying, is whenever the two transistors are conducting at the same time, because during the transition, there is a moment where the P transistor and the N transistor are both conducting, so there is a current going there, so there are some dissipation. And the world is demanding low power. Yeah, we know that the world is demanding low power, and it is economic, it is political issue, it is sustainability issue, so everyone is talking about low power. This is the reason that it's very important to understand how to reduce the power, because it's very easy to talk about low power, how we do that. So leakage definition, so the leakage current is a current that flows due to mainly instability to the short of transistor, is based on manufacturing, is not changeable, and is depend exactly on the manufacturer. Okay, so this is the the reason that leakage is something that we cannot address from the design point of view. And more leakage, less power. So we are doing more and more leakage, and we are having more and more power problems. So the leakage problem, the technology trends result in increases leakage. So going down in technology, we are increasing the leakage, advanced processes and reduced supply voltage. Yeah, because we are also reducing the voltage. And we are going to see that this is a very well-known technology to reduce the power, because the power also depends on the voltage, on VDD. So reducing the power will help reducing VDD, but at the same time, it increases the leakage problem. So the market demands decrease leakage. How we do that? So the longest battery life for wireless and customer market, but so we need to not only to reduce the dynamic power, but also the static power. So more performance for high performance make trade-off. And this is the reason that some companies, they have the different VTs. The leakage current depend a lot on the threshold voltage. So you have TSMC that you have different kind of VTs. So you can choose the one that depends, the one that will be the best for your need. So leakage reduction, we minimize leakage in standby mode, leakage in active mode, and so on. Performance penalty, area penalty. So when we try to reduce the leakage, we will have some penalties on performance, area, and dynamic power over here. So summary of leakage. Leakage is now a major problem, even if now with the FinFET that only get around, it could be a little better. The battery life issues for wireless application that are dependent not on leakage, and the total power budget for wire application. A leakage problem cannot be solved by new processes. Design approach are needed to minimize leakage. So we need to think on design, and we are going to see, and design engineering to the rescue, because the process will not change. So what are the techniques to do low power? As I was saying, while leading companies were searching for other sources of low power, I see designers only one way to meet the market demands. They have to find new ways to reduce IC power, and by its application design super low power ICs. So this is the role of designer today. Find a way to do low power ICs. And energy efficiency design is a critical everywhere. We have the low power that is a market differentiation, but is also the power constraint. So we see more and more that we need, let's look the electrical car as an example. What we want from an electrical car is autonomy. How many kilometers I can do with one charge of the battery? 200, 300 kilometers, 500? And how long it will take for me to charge the vehicle as well? So this is one of the problems that electrical vehicles are having in some countries. They say, it's too long, it's too complicated to charge. And after, what about autonomy? So this is the reason that low power has become also a differentiation from the market point of view. So there are different challenges on energy efficiency design. We need to minimize the power. We need to grow the in design areas and so on, so on. So we need to be sure that we combine the different constraints, thinking that today power has become, this is historical. At the beginning, when we were doing design, area was the first constraint and the most important. After we went to speed, and now we are going to power. Okay, and there is a relation between the three things that we are going to see. So if you reduce the speed, you are going to increase area. But if you reduce also, if you increase the speed, you are going to impact power. So there is this ratio between, this compromise between these three variables. So there is also something very important that is appearing in the market, is the shift left for low power and energy efficiency. What we used to do was, let's wait to the end to see how power is performing. After we put some design constraint, we put clock gating and other kind of technology we are going to see. But now, the question is the following. I'm saying the dynamic power is coming when you have a transition from 0 to 1 or 1 to 0. Who produced the transition? The software. So what about if we optimize the software for low power? Reducing the number of transitions. There are ways to, when you compile a C program, you can put some options, minus O1, minus O2. And this is the compiler. We are telling the compiler, optimize the code. Okay? Because when we write code, we don't care about how many transitions we are going to produce. So that is going also to produce power. So going, also there is something today we talk a lot about software, hardware co-design. What we do in software, what we do in hardware. So there's also a decision at that level of the design, at that level of the system design, to say, okay, I'm going to do that in software, I'm going to do that in hardware, taking in account the power as well. So this is, we have a different kind of tools. I need to do some publicity, because if not, Synopsys will not continue paying my travel. So we have different kind of tools at the different levels of design to work on power and to analyze the power. But do not forget that even with artificial intelligence, the designer is the one that has to make the decision. We have a lot of tools that use Gen AI, but the designer is the one that will make the final decision. So power reduction, so we have the active, the leakage, and so on. We have different technologies. We are going to visit some of them now, how to reduce the power, and how to be sure that we are getting good results. So dynamic FER, the first one is logic design sizing. We can have different, the size of a gate will impact on the dissipation of power. So we can change the device size to be sure to consume less power, because at the end, what is consuming is also the transistor. The bigger the transistor, the more we have the consumption. So we can also restructure the logic. Like here, we have an example. We have a 3-level netlist gate, and we have 2 levels. So we can also do these kind of things without ignoring glitch effects. And I'm working right now on a very interesting topic with one student. I started that when I was working at Giovanni Micheli laboratory, is how to do technology mapping power aware. I explain it one second. Technology mapping is when you take this netlist that is generic, not yet associated to a library, and you start mapping to a specific library, putting constraint. So today we have algorithm for size and for speed, and we use, for power, we only work on flip-flops and latches. But there are gates there are combination of gates that will dissipate less than others. So we are working right now in an algorithm to reduce that and try to find out what is the best configuration in gates to dissipate less power. Yeah, I hope we will get some results. It's not sure. It's not sure, because it depends on a lot of parameters that are very, very hard to compute. So the second one is reduce VDD. Okay, if we reduce, because the power is C, the load multiplied by the VDD, the square of VDD. So if you reduce the VDD, you reduce the power, of course, but no effect on area. It's a quadratic function of that. But decreasing in supply voltage increase the speed. Sorry, increase the overall delay. So reduce the speed of the circuit. So yeah, you can reduce power by reducing voltage, but there is a moment that you are going to affect the speed of your circuit. Another one is as a function of VDD, so decreasing. Yeah. Okay. No, this one. Okay. So as I just say, decreasing VDD will help, but will produce problems. So what we do is to use multi-voltage design techniques. So we define that in the same chip, we are going to have different areas to have different voltages. For example, one part that I need high speed, I will put more voltage. One part of the circuit where I need less speed, I will put less voltage. But this is not easy, because I have, when you cross areas, because signal will cross areas with different voltage, you have to put some special cells to convert the voltage from one level to the other. It's not just to connect, because if you just connect the cells in different voltage, you are going to create problems. So this is one of the problems, which is this is the chief register, chief level register. Chief level register, where you change the power. So reducing voltage decrease the power significantly, but it creates problem with the speed. At lower voltage, the delay increases very significant, and this is the reason we are now implementing this multi-voltage designs. Next one is clock gating. This is one of the most famous things. So we say that the dynamic power is being there is dissipation when there is a transition between 0, 1 or 1 or 0. But sometimes we know exactly that there will be no transition on the output of a flip-flop. The output of flip-flop will remain the same, will be 0 or 1. So we can stop the clock at that moment. So this is clock gating. We stop the clock at a specific moment so the flip-flop will not have any kind of transition. So we don't dissipate. Because if the clock is there, there is a transition even if the output doesn't change. We are going from 0 to 0 because the transistor will be capturing the input and will change to the same level, but we are going to have dissipation. So a significant fraction of dynamic power in a chip is the distribution network to the clock. Up to 50% or even more of dynamic power can be spent in the clock buffers. This is the reason that we reduce that. And it is important to understand how you decide or how the tools will decide which flip-flop we can gate. We can put a clock gate. So it's based on simulation because it is based on switching activity. Switching activity is the number of transitions that a flip-flop will have. And for that, you do estimation, probabilistic estimation, or you do simulation to get the results. So this is the way we do that. So we finally, we are putting a clock gate that will stop, will disable the clock whenever we need to that. So we don't apply that to any flip-flop. It has to be at least 50% transition. It has to be on a bus because for one flip-flop is not worth the value because we are adding more electronic to do that. So there is a lot of condition to do that, and the tools that the EDA vendors produce are doing that work for the designer. Of course, the designer has to verify that everything is working well after, because the clock gating is creating other kind of problems. One day we were analyzing, without clock gating, the one small design, very small, very small circuit, 4 or 5 gates, we were reducing that to just one wire connected to VDD. If we were putting clock gating, that optimization was no longer possible. So there is a lot of consideration. So the designer has to take care of looking at that. Okay, there are several clock gating styles. There is, and today we are implementing a new one, which is a sequential clock gating. You have the self-gating, meaning that you analyze the input and the output through an XOR gate to know if there are changes, or there are the sequential. So knowing that this one will not change, so that one will not change either. So there's a lot of technologies to do that. After we have the dynamic voltage and frequency change, scaling. So in a circuit, based on what we are doing, this is the reason we have a power control area, which is the yellow one. Based on the functionality, at a given moment, we define the frequency and the voltage that is applied to each block of the circuit. It's very difficult to design that. So the tools will help, but in general, we are having a dynamic voltage and frequency scaling. So we change that based on the needs. So dynamic, okay. Okay, now we go a little to the leakage, which is a little more complicated to reduce. There are some, okay, this is the self-reverse bias that we were talking a little before. So we change a little the VT to decrease the leakage. The one that I like is the multi-VT. As I was saying, the voltage threshold, the manufacturing, so will produce different kind of VTs, so you will have different leakage. Okay, so this is the threshold change, trade-off between leakage and delay. Of course, when you change the VT, you are increasing the delay. When you increase the VT, you decrease the delay, and so on. So there is a compromise between. And this is the reason people are also using these different VDDs. So we are trying to get the compromise of this by changing the different, okay, the multi-threaded logic. So you use different VT, and if you see, for example, TSMC for the same technology, they will have the low VT, medium VT, high VT, and you can, because it is the same technology, you can have the different kind of cells in the same chip. You can have one part of the chip with low VT, another one with high VT. Same technology, because you cannot change the technology. It's just a change of the cells of the library. There is the sleep transistor. You put some transistor to sleep in order that some part of the circuit is not connected anymore to VDD. So you sleep some transistor and you get less leakage current. This is very, very well known in FinFET. Okay, the advantage of that is effect for standby, voltage reduction, so on. And there is the power gating. Also, not only we put different VDDs on a circuit, but we also switch off part of the circuit for a moment. When we know that there is we have the possibility to switch off part of the circuit, we do that. So, for example, here you see that this white part of the circuit is switched off. So there is no activity. And there is also complication, as we say, multi VDD, the power off of part of the circuit, because you have, when the circuit is switched on, you have to recover the state of that part. So meaning, and I always put the same example, if you look at the watches, or even the cell phone is, the screen is sleeping for a moment. But when I switch on, I want to see my clock working with the same time. So we have what we call the retention register. So those are registers that will retain part of the information, so I can recover the state of the circuit when I switch on. Okay, there are a lot of architectural trade-off, and it is so this is an important part of the design, because the designer will have to decide from the beginning, which part will be on switch on, switch off, which part will be in which VDD, and those are, so the decision that the designer is making will go over the complete flow. And there is a language called UPF, Unified Power Format, that where you define all those constraints and all those variables that will go through all the tools in your design. Okay, power gating, also we are, let's say we try to stop part of the circuit, putting some transistor there that will sleep. A lot of challenges. Okay, we have to define a strategy. You have to be sure that it works. You have to be sure that you recover the state of the circuit whenever you switch on, etc., etc., etc. And okay, this one, variable threshold. We can have a variable VT that is used in FinFET also, that will reduce the leakage current. And now let's go for some conclusion. And after, so this for me is very, that picture appeared on a German newspaper a long time ago. So what is the purpose to have electrical car if we are producing electricity from fuel? So when we talk about low power, we are talking about, and we talk about sustainability and all that, we're also talking about how we get the power, how we get the energy. So this is the reason we talk about low power, energy efficiency as well, because we need to reduce that to avoid this kind of ridiculous situation. So some remark, low power is one of the key challenges on IC design today, digital IC design. It reduces the heat and the climate consequences as well. So when we talk about climate change, this city got a lot of problem a few months ago with the flood and all that, the water. This is based on, even if there are politicians that say that climate change is not true, it is true. Okay, it is true. There is a climate change, and part of that is coming from energy. As I say, 40% of the CO2 that is sent to the atmosphere is coming from energy manufacturers. Energy, as I say, is the most important CO2 generator. Different techniques to ensure low power, but the designer has to choose the right one for the specific design. It's not, I will apply everything. Need to choose based on design and application constraint. And finally, IoT and edge compute need low power. Okay, thank you very much for your attention. And by the way, technology is not always working. They want to have lunch.
Questions?
Lunch. This is not the question. Lunch. What is lunch? That's the question.
Well, we are already late, so
Yeah, let's go. Yeah, no problem.
so we go for lunch now, and then 1:30, let's say 1:29. Let's be here to start the session. Start from 5 and choose one time space for the after the casting here. We have a microbus that will bring the speakers and so on. So see you at the before 1:30. Eu mandei um e-mail lá. Oi, mandando um eu mandei pro Rio lá no
Beleza. É verdade, um monte de agora tá. Tudo bem?
So let's go.
Mas dá um 6 meses. Mas eu tenho 4
Let's go.
Agora eu tô sem computadores.
Vamos.
Lá em São Paulo.